Let's look at part B of 2018 final exam paper. We will only focus on questions B1 and B2. So looking at question 1, it is dealing with a compression spring. So a helical compression spring is to be designed using 5 mm diameter music wire, which has a spring index of 10. Solid length is given as 60 mm, and the spring is having ends which are plain in nature. It is estimated that a force of 300 Newton will compress the spring to closure. So you have to determine the number of active coils, the spring rate, the free length, the maximum shear stress, and finally the static factor of safety. So what we do is, whenever we get a question of this sort, we try to identify the variables and qualitative data that is given to us. So we have a helical spring which is made using a 5 mm diameter wire, right? So wire diameter is given as 5 mm. The spring is made from music wire. So again, this is very important parameter that we need to understand. The spring index is given as 10. The solid length is given as 60 mm. So we are identifying all the quantitative and qualitative information. The ends are left plain, so we've got a plain end scenario. It is estimated that a force of 300 Newton causes the spring to compress to closure. So that means this 300 Newton is the maximum force that is required to fully compress the spring to its solid length. So solid length is given, the maximum force that we're looking at is given. So now let's start solving this problem. So as mentioned earlier, the first thing is you need to list down the variables that are given to you. So wire diameter was 5 mm, spring index was 10, and we know that your spring index C is equals to capital D over D, where capital D is your spring diameter, small d is your wire diameter. So therefore your spring diameter is 50 mm. The maximum force, this 300 Newton becomes your maximum force because it says that this 300 Newton completely compresses the spring to its solid length. So there's a maximum force that you will deal with. The solid length was given as 60 mm. For plain ends, what we can do is we can get this information, and since it was a music wire, we can also get this information. So what I'll do is we will refer to table 10-1, 10-4 and 10-5 for obtaining this information that we have over here. So what I normally do is I list them in the beginning, but if you want to solve them step by step as the question appears, you can do so. In the next few slides, I will have these tables appear once more so that you are able to understand from where I'm picking this information and as to how I'm picking this information. So let's move on. So this is the first step, to list all the variables and also list the qualitative information that is given to you. With respect to this qualitative information, we can get these values. So now let's look at question 1. It says that we are to find the number of active coils. So we know that we have plain ends. So for plain ends, in table 10-1, we can go to this table and then look for the column which contains information for plain ends. And in this table, we are only going to look at the relationship between total coils and then the solid length. So when I read information from this table, you'll see that your solid length L0 is simply equal to D into NT plus 1. So this is what I have here. Sorry, my solid length LS is given as D. LS is equals to D into NT plus 1. I know my solid length was given as 60 mm. The wire diameter was 5 mm, so into NT plus 1. So once I solve this, I get my NT to be 11. So this is what I get in the beginning, right? My NT is equals to 11. So what you had to do is you had to find the active coils. So again, going back to this table, you'll see that your total coils NT is simply your NA. So what this simply says is that your active coils NA is simply equal to NT. So therefore I have this equality coming over here. So basically the number of active coils is simply equals to your NT, which is 11. So this is the first part. The next part is that you have to find your spring rate, and the equation for finding your spring rate is simply given as small k. So this is spring rate. So some of you make a mistake, students in the past make mistakes over here. Your spring rate is small k, right? So your small k is equals to wire diameter to the power 4 times your modulus of rigidity divided by 8 spring diameter cubed into Na. Now what happens is, this we don't know. We know our wire diameter, we know our spring diameter, now we know our Na from the previous step. So we had to find the value of modulus of rigidity. So how do we do that? For this we have to refer to table 10-5. So what happens is, the spring was made from music wire, so that's why I have to refer to this material over here. So qualitative data that was given was music wire. So now for music wire, what I can do is I can read my values. So modulus of rigidity is contained in this particular column, which is the last column. So what we have is, we've got multiple values that are given. So how do we fix our value? So it's very simple. In this column, diameter, which is given in inches, what we do is, whatever wire diameter was given to us, convert that into inches and see in which range does that fall. So for us, our wire diameter was given as 5 mm, and to convert mm to inches, we simply divide it by 25 mm. So 5 divided by 25 gives us a value of 0.2. So when we look at 0.2, so 0.2 falls in this range. So all the values that are greater than 0.125, so 0.2 is greater than 0.125, and corresponding to this we get a value of 80 gigapascal. So again, when you refer to this table, it's basically whatever spring wire diameter was given, you have to divide it by 25, because that's how we convert mm to inches. So here what I have done is, I have done 5 divided by 25, and once I did that, I got a value of 0.2. So I have to see where does this fall. So 0.2 is greater than this, and therefore modulus of rigidity is 80. So that's how this 80 is brought over here. So substituting all the values now, I get my spring rate or the spring stiffness to be 4545.45 Newton meter, right? So just ensure that this is not mm, this is Newton meter. So just make a correction over here. It is not Newton mm but Newton meters. This value is correct, but the unit is incorrect. So just make a change that it's Newton meter. Now the next part was, you have to find your free length. So the first thing is, we need to understand the relationship between your free length and your solid length. So your free length is simply given by this relation, and this relation we have obtained in our lectures. So your free length L0 is simply given as your solid length plus your maximum deflection. So this diagram, this figure over here explains the relationship. So the free length is the length of the spring when there is no force acting, and solid length is a scenario in which all the coils of the spring are in contact with each other. So now you see the difference between the free length and the solid length gives you your maximum deflection, which is your Ymax. So what happens is, so basically the free length of a spring is simply equals to the solid length plus the maximum deflection of that particular spring. So this is what I have here. So what I have is, my solid length was 60 mm. So again, students make a lot of mistake over here. So what I normally do is, I convert everything into SI units, is basically in meters. So 60 mm, trying to convert it to meters. So basically you can do 60 divided by 1000, or you can say 60 times 10 to the power of -3 plus. Now what happens is, why I'm using a force of 300, and you know that your force is equals to Ky. So force is equals to ky, this relation is also true, and then y is equals to F over k. Since I'm dealing with y max over here, so it will become F max over here. So F max was 300, right? A spring rate was already calculated in the previous step. So what I get is my free length is 0.126 meters, or which is 126 mm. So this equation that we have obtained here is obtained from this diagram, and this is something that we had done earlier in our lectures. So again, just keep this in mind, that is very important. Moving on, the next part of the question required us to find our maximum shear stress. So your maximum shear stress tau max is given by this relation, which is 8kfd divided by pi d cube. So in this, you see you've got a capital K, and capital K is your stress concentration factor, small k is your spring rate, and capital K is your stress concentration factor. Again, students previously have made mistakes between these two K, so I always tell you that you need to distinguish between small and capital K. So your capital K, your stress concentration factor, is simply given as 4C plus 2 divided by 4C minus 3. C is your spring index. In this case it was 10, so 4 times 10 is 40, plus 2 becomes 42, and 40 minus 3 is 37. So your stress concentration factor came to be 1.135. Now substitute everything into this equation. 8 times k times your F max again, because we're looking at tau max, and then your spring diameter was 50 mm, wire diameter was 5 mm. So substitute all these variables in this equation, and you get your maximum shear stress to be 346.83 megapascal. Now the last part is you have to calculate your static factor of safety, and your static factor of safety is basically your SSY divided by tau max. So tau max we have already obtained as such, so we have to calculate our SSY, and SSY is our torsional yield strength. So in order to calculate this, we have to follow this particular step. So the first thing is we have to find our ultimate tensile strength, which is your SUT, and SUT is simply given by I divided by dm. So now you will say that how did I obtain these values over here? So we know that we were given a spring which was made using music wire. So in table 10-4 we've got music wire, and we look at the values of M, right? So for M was 0.145, and I will use this value, and I is given as in megapascal dot mm to the power of m, right? So basically this small m is your exponent, so this value is 2216 megapascal mm to the power of m. Now you'll see that in this equation I'm just using this value straight away, because what happens is, the thing that you need to keep in mind is this is 2211 megapascal mm, and then what happens is D is the wire diameter in mm. So that's how I can use this. So be very careful. Most of the time students make mistakes here, because instead of using your wire diameter in mm, they convert it to meters, and once they do this division, this value becomes too large. So very careful that when you use this equation, your D has to be, your wire diameter has to be mm, and the reason why it has to be in mm is because the value or unit for I is in megapascal mm. So that's why your wire diameter has to be in mm. So once you substitute these values, you get your SUT. Once you do this calculation, whatever value you get, it will be in megapascal. So you obtain a value of 1750.8 megapascal. Now the next thing is you have to calculate your SSY. So the maximum stress that a spring can be designed for, that can cater, is your torsional yield strength. And again what we do is referring to table 10-5, looking for music wire. So here your elastic limits, percentage of SUT. So this column is for tension and this column is for your torsion. So we always look at the torsional yield strength, and what we have is we have a range that is given to us. So your torsional yield strength can range from 45 to 60%. For us, we always use the upper limit. So that's why your SSY is simply going to be 0.6 SUT because 60%. So I'm not going, it's basically 60% of SUT. So basically 60% is 0.6 and SUT we had already calculated. So your maximum, sorry, not maximum, but your torsional yield strength is 1050.48 megapascal. And finally what we do is your static factor of safety is nothing but SSY over tau max. So once you do this calculation, you get your static factor of safety to be 3.03. Static factor of safety does not have any unit, so it is just that. So I hope now you understand how this simple problem was solved. There's a lot of referring to tables, looking for values and so on, so be very careful when you solve this type of problem. Now let's move on to question 2. Question 2 part A is looking at design of a compound riveted gear train. So you have to design a compound rivet gear train which gives you a speed increase of 80:1 and the pressure angle is given as 25. So whenever you're given this type of a problem, so the first thing that you do is you look at the speed increase that you are required and also looking at the pressure angle that you're dealing with. So what we did is, the first thing that we do is we draw a schematic of the gearbox that you have to construct. So this does not need to be to scale, just to help you out as to what you're doing. So I have my gear 2, gear 3, gear 4 and gear 5. So gear 2 drives gear 3. Gear 3 and gear 4 are fixed to a common shaft, so the speed of gear 4 is same as gear 3. And then finally gear 4 drives gear 5 and the input and the output shaft are in line. Now what happens is, what we do is we need to follow certain steps in order to solve this problem. So the first thing is that when we're looking at our steps as discussed in our lectures, so the first step was to list all the combinations. So what we have is we're looking at 80:1, so we can list all the combinations. For instance, 1:80, 2:40 and so on, and then we'll end up till 80:1. So then after listing the combination, we have to select a combination for which your ES1 is greater than ES2. So the first stage strain value has to be greater than the second stage strain value. So we'll look at combinations, let's say from 10:4 and so on, something of 10:8 and so on, or maybe 4:20:4 and so on, right? So those combinations. So the next thing is, the next point says that ES1 has to be fairly equal to ES2, right? So after doing the first 3 steps, I was able to determine that my ES1 is going to be 10 and my ES2 is going to be 8. So then what happens is you have to find your NP, which is the minimum number of teeth on the pinion, to avoid interference. And then what happens is the formula for this requires that we know our M, and M is nothing but your first stage strain value. So here this is what I have. After going through steps 1 to 3, I said that my combination is 10:8 and ES1 is 10 and ES2 is 8. So now this formula will be given, or you have to use this formula to find your NP. So K over here is the tooth depth, and it is always assumed to be 1 unless until specified otherwise. So M is same as your ES1, so M was 10. So again, when people solve this, this is very important. When you look at this expression, it is 1 plus 2 into M, then all of this is multiplied to sine squared phi. So some of you, what you do is you'll say 1 plus 2 times 10 is 20. You'll do 1 plus 20 sine squared phi, which is wrong. That's not the case. So that's what I have over here. It is 1 plus 2m, whatever value you get, it is then multiplied to sine squared 25 over here. So 2 times 10 is 20, 20 plus 1 is 21, so 21 sine squared 25. So substituting all the values, M is 10 into this expression, I get my NP to be 10.76. and then you need to understand that we always round NP up to the next integer, not the nearest but the next. So in this case the next integer is 11. For instance, if your NP here was, let's say, 10.005, right, 10.005, again you will round it up to the next integer, not the nearest but the next. So again your NP would have been 11. So this point is very important. This step is very important for you to understand. Now moving on, what happens is, let's look at step 5, 6 and 7. So what we have is step 5, ES1 is equals to N2 over N3, so that's equation 1. ES2 is equals to N4 over N5, that's equation 2. So what happens is, when you look at this, your train value is nothing but product of driving tooth number divided by product of driven tooth number. So in this stage, in stage 1, the driving tooth is N2 and driven tooth is N3, and in this stage the driving tooth is N4 and driven tooth is N5. So therefore in this case ES1 is simply driving, which is N2, and divided by driven, which is N3. So ES1 is N2 over N3, and in this case ES2 is simply equals to N4 over N5. So this is what I have over here. And then step 6, N2 plus N3 is equals to N4 plus N5, that's equation 3. And then step 7, we sub 1 and 2, equations 1 and 2 into 3, and then we obtain equation 4. So let's see, ES1 is equals to 10 is equals to N2 over N3, therefore N2 is 10 and 3, so that's equation 1. In the similar manner, ES2 is equals to 8, which is equals to N4 over N5, so N4 is simply 8 and 5, so that's equation 2. This is equation 3, and this equation we're using because we're saying that we need to have a compound riveted gear train, and another fancy name for compound riveted gear train is simply when your output and input shaft are inline. So when we have this restriction, we have this equation as well. So N2 plus N3, number of tooth on gear 2 plus number of tooth on gear 3 should be equals to number of tooth on gear 4 plus number of tooth on gear 5. So we have this, and we can substitute equation 1 and 2 into equation 3. So N2 is 10 and 3, so there, plus N3 is equals to N4, which is simply 8 and 5. Done. So we end up with equation 4, which says that 11 and 3 is equals to 9 and 5. Now let's move on to step 8. Step 8 says that we have to minimize the smallest gear in the largest train, which is basically the smallest gear will be N3. So what we do is we set N3 is equals to 1 in equation 4, and then we solve. So basically this is known as a normalization. So basically set N3 is equals to 1, equation 4. So 11 N3 is equals to 9 N5. So substituting, we get N5 is equals to 11 over 9. So now how do we proceed from here? So let's look at our steps 9 and 10. So N5 will be equals to I over B, which will be an improper fraction. So we need to ensure that I over B is in simplest form. So what simply means it cannot be simplified furthermore. So when we look at this 11 over 9, we cannot further simplify this. Then we move to step 10. Choose N3 such that it is multiple of B, which is your denominator, and also greater than NP. So this is where this statement comes up. So therefore N3 should be multiple of B. So B was 9 in its simplified form, and it should be also be greater than equal to 11. So what you have is multiples of 9 will be 9, 18 and 27, and at the same time it has to be greater than NP, which was 11. So the logical choice is 18. So your N3 is 18. Then what we can do is we can solve for the other gears. So N2 is 10 and 3 as given by equation 1. So your N2 is 180. Then what we have is using equation 4, 11 and 3 is equals to 9 and 5. We can solve for N5 because N3 is 18, so we get 22. And finally N4 is simply 8 and 5. We are using equation 2, so we get 176. So the final step that we need to look at is basically to verify whether our calculation is correct. So N2 plus N3 should be equals to N4 plus N5. So 180 plus 18 is 198, and 176 plus 22 is again 198. So this is how you verify that your solution was correct. So again, as long as you stick to the steps that we had looked at in our lectures, you should be able to handle this problem quite easily. The trick is to understand how you calculate your NP. NP is always rounded up to the next integer, not the nearest. So this is a very important point over here. And finally, in this stage, once you normalize and you get N5 is equals to A over B, ensure that A over B is in its simplest form. Then what happens is, whatever denominator you get, that's the multiple that you're looking at, and in addition to that, your N3 has to be multiple of 9 in this case, and also greater than NP, which was 11. Now let's look at question B2B. What we have is, we have a cam with a minimum radius of 20 mm. It is rotating clockwise. So what happens is, the mean radius is 20 mm, so that is a very important information, and at the same time it is rotating clockwise. This information will be helpful when we draw our cam profile with a uniform speed of 300 revolutions per minute. The cam is designed to give a knife edge follower at the end of the valve rod the following motion. It says that to keep the valve closed during 60 degrees rotation of the cam. Then what happens is, to raise the valve through 40 mm during 120 rotations of the cam, and then lower the valve during the next 120 rotation of the cam, and finally keep the valve closed during the remaining rotation of the cam. So what happens is, when we look at this, I can say that the first 60 degrees rotation, the valve is closed. The next 120 degrees rotation, the valve is open. For the next, it is being closed, and then step 4, it remains closed. The displacement of the valve while being raised and lowered undergoes a simple harmonic motion. So this becomes very important. So the motion is a simple harmonic motion. So this will actually help you to determine as to which method you will use to draw your displacement diagram. And then again it says raise the valve through 40 mm. So this 40 mm becomes your maximum stroke, is the maximum distance that the the knife edge follower moves. So the first thing is, you have to draw the displacement diagram, and the second thing is to draw the displacement diagram using a scale of 10 mm represents 30 degrees, and finally draw the cam profile. So the first thing is that we have to draw our displacement diagram. So we need to understand that we're given a simple harmonic motion, right? So for simple harmonic motion, what we do is, there are certain steps that we need to follow. So what we do is, on our x-axis we represent the rotational degree, and on our y-axis we represent our stroke. So this distance from here to here is basically your stroke, and your stroke was simply 40 mm. So you don't scale your stroke, you will leave it as it is. So you will leave it as 40 mm, right? So this will be actually 40 mm. So you will measure 40 mm on your paper and put it as it is. Now what happens is, the scale was given which says that every 10 mm represents 30 degree rotation of the cam itself. So what happens is, in the beginning remains closed for 60 degrees. Outstroke, this is when your valve is opened, is for 120 degrees. Then the valve is closed for the next 120 degrees, and the valve remains closed for the next 60 degrees of the rotation. So what happens is, using a scale of 10 mm is equals to 30 degrees, we have to get the linear dimensions in on our x-axis. So 60 degrees, 10 mm represents 30 degrees. So how much is 60 degrees? So 60 degrees is basically 20 mm. 120 degrees is 40 mm. And then finally 60 degrees is again 20 mm. So what we do is, we draw our stroke which was 40 mm, leave it as it is. Exactly, you don't scale it. Then on our x-axis, what we'll do is, I will draw a distance of 20 mm. Then from here to this point I will measure 40 mm, and then from this distance over here I will measure another 40 mm, and then finally for the remaining rotation it is 20 mm, which represents 60 degrees. Once done, what I will do is, I will draw my blocks in at this location, so they will become my first building block before I do anything further. So then what I do is, for simple harmonic motion, we divide the stroke circle or the stroke semicircle into 6 equal parts, right? Very important. For simple harmonic motion, we don't divide the stroke into 6 equal parts, but we divide the stroke circle, or basically this semicircle, into 6 equal parts. And in MM101 you already know how to do that division. So from the center of the stroke, draw a circle. Once you have that, draw this line across, and then what you do is you keep in your compass the distance, which is simply radius, equals to the radius. So cut, and then from here you can cut this point, and you can divide this semicircle into 6 equal parts. Then what we do is, wherever you have made those cuts on this semicircle, you will draw projecting horizontal lines right across as such, and then you will do the labeling. The reason why I do the labeling is that I understand what I'm actually doing. So what I'll do is, so 1 2 3 up till 7, in the same manner I will, since I'm dividing this into 6 equal parts, what I'll do is I will divide this portion into 6 equal parts as well. So 1 2 3 4 5 6, and the manner in which I divide this is basically using this technique. So divide this line into, let's say, 6 equal parts, right? And then let's say this is the last one, so join it over here, and then you project these lines over here accordingly, right? So you can do that. I don't want to show that. All of this is shown in your lecture itself. So I will divide this into 6 equal parts, and then this is your return stroke. Again, I will divide that into 6 equal parts, because I'm dividing my semicircle over here, stroke semicircle, into 6 equal parts. And then finally label them 1 2 3 4 5 6 7, and then this is in the opposite order. So what I do is I can fix for my points. So 1 1 is over here, so this is horizontal line 2, this is vertical line 2, so that becomes my other point. Horizontal line 3, vertical line 3, so on I can get my points in. And then over here 6 6, and then what I do is I join these points using a smooth curve. Keep in mind, most of the time students make a mistake. They will have this curve darkened, but they forget about this portion and this portion. So your displacement diagram is all of these, so all the curves need to be darkened. So that's how you will draw your displacement diagram. And finally, when we have to draw our cam profile is quite easy. So I mentioned in the beginning that the cam is rotating in the clockwise direction. So when you draw your cam profile, you have to go in the opposite direction. So we have to go in the counterclockwise direction. So that's why I have indicated an arrow over here. So what happens is, you'll see that I've got a blue circle and a red circle. So this blue circle is basically your minimum radius, which was 20 mm. So from the center I will measure 20 mm and I'll make a circle of radius 20 mm, and then this red circle is basically, this is your base circle or your cam radius, and then this red circle can be simply drawn by taking into account that the maximum stroke or the maximum rise is given as just 40 mm. So what I can do is, from this point over here measure a distance of 40 mm, done. And then from this center extend your compass over here and draw a circle. So this becomes your maximum stroke circle. So what happens is, between this maximum stroke circle and this your minimum cam radius, this is between these, this is very important, because between these two circles you will have your cam profile. Now what happens is, the manner in which I will draw my cam profile is, again, the first thing is you need to divide this into the 4 blocks, and those 4 blocks are with respect to what we did over here. So the first thing was you had a dwell of beginning of 60 degrees, so done. Then from this point onwards you had 120 degrees rotation of the cam in which the follower was moving outside. So you can see from this point to here I have 120 degrees, and then what happens is for the next 120 degrees rotation of the cam, the follower is going back to its original position. So you'll see that from this point to this point is another 120 degrees, right? And then finally for the remaining rotation of the cam, which equated to 60 degrees, the follow or the valve will remain closed. So these are my 4 blocks that I was dealing with. So this is 1, then from here to here is 2, from here to here is 3, and then from here to here is 4. Now what happens is between these 120 degrees rotation, with reference to your displacement diagram, I divided here into 6 equal parts, right? So 1 2 3 4 5 6. So there's the same thing that I need to do here. So you have to divide 120 degrees into 6 equal parts. So basically 120 divided by 6 gives me 20 degrees. So all of these increments in between this region, right, that you see over here is divided into increments of 20 degrees. So 20, 40, 60, 80, 100 and 120. Now the next thing is as to how I get these points in. So getting these points in is very easy. So basically from here to here, the cam was rotating and there was no movement of the follower. It remained stationary, so dwell. Then from 60 degrees onwards, the follower moves outward for the next 120 rotations of the cam. So this point over here is basically a point over here, right? So your minimum cam radius is basically indicating this benchmark over here. So what I can do is then this is my 1, right? This is 2, this is 3, this is 4 over here. So this one is reference to 1 over here. So when I pick this distance and put it over here on this radial line over here, I would be just at the cam radius. Now let's look at point 2. So point 2 is over here, so I measure this distance on my compass, and then this is the radiating line or radial line for point 2, taking my distance from my base cycle, which is your basically your cam radius. So from base cycle, which is blue, taking the distance, cut it on this radiating line. Same thing, I go to, let's say, 4. So 4 is this distance, measure it using my compass, come back to this. So radiating line or radial line for point 4 is here, base cycle is here, put my compass here and cut this radiating line at this point, and so on. Once I get my points in, I can join all the points using a smooth curve. So same thing on this side, and finally for the last 60 degrees rotation, the valve remains closed, so it is basically on your base cycle, and I get my cam profile. So when you're doing this cam profile, the things that you need to keep in mind is that you need to indicate the direction in which you're drawing your cam profile. So your cam was rotating clockwise, so your cam profile will be drawn in the counterclockwise direction. Keep that in mind and then indicate this direction. You don't need to put the 60 degrees and so on. I'm just doing that so you understand as to how I've got my cam profile in. So that's basically looking at the first 2 questions of your final exam paper. So thank you.